SwayamPrabha. Digital India. Educated India.
Hello, welcome back to the lecture 13, which is a continuation of the previous lecture. Here we will solve certain examples on thin wall cross section shaft using the membrane analogy that we have discussed earlier. So, let us first solve this example. In this example, there are two tubes, both are annular tubes, but in one of the tube there is a slit. So, this is the closed annular tube. Okay, this is a perfect circle. So, although I haven't drawn it as a circle, so the mean diameter, that is the diameter of the center line of this annular cross section, is D, which is given as 16 T. T is the uniform thickness of the annular tube. So, T is uniform all through the annular tube. Okay. So, this is the closed annular tube, and there is another cross section which is the same annular tube, but there is a small slit here. So, a small slit here. So, there is a slit. So, the slits are in the slit is such that they are in contact with each other, but they are not closed. A small cut is there on the annular tube. So, we therefore have two such cross section. The first cross section is closed annular cross section, and the second one is annular cross section with a slit. Now, we need to find out the ratio of the angle of twist for both these cases and the maximum shear stress for both these cases. So, if theta C is the angle of twist here, angle of twist or rate of angle of twist, whatever way, both will eventually just be similar, and theta S is the angle of twist here. So, the first thing we need to do is to find out the ratio of theta S by theta C. This is the first thing that we need to find, and the second thing is that if tau C is the maximum shear stress here, and tau S is the maximum shear stress, then we need to find out the ratio of tau S by tau C. So, this is what the problem asks for. So, let us see how to solve this system. So, the first thing let us do is to analyze a annular cross section with a slit and find out theta S and tau S. Now, you will be able to appreciate that a annular cross section with a slit is actually an open cross section. Okay, it is not a closed cross section. Therefore, we can use the formula that we have derived for thin walled open cross section directly here. So, according to the formulas that we have derived using the same membrane analogy for thin open walled cross section, we can say that the torque T, which is basically mt, we have been calling it mt all the while. So, T is given as 1/3 Bt cube into g theta. We have seen this. We have seen earlier that the torque, the expression for torque for a thin walled open cross section is given as 1/3 Bt cube, where T is the thickness and B is the length. Now, therefore, if we apply it for a annular cross section with a mean diameter d, then this becomes 1/3 g theta. Theta will be theta s, so theta s, and t is t, b is pi into capital D, d being the mean diameter into t cube. So, if I write this, this will be 1/3 g theta s pi into 16 t to the power 4. So, from this we get theta s as 3t by pi g into 16 t to the power 4. So, this is the expression for the angle of twist or rate of angle of twist for an annular cross section, with d we know is given as 16t. So, we know therefore, theta s for an angular cross section is just 3t by pi g into 16t to the power 4. Now, let us see what is for a close cross section annular structure. Or before moving into this, let us find out the shear stress also. So, let me find out the maximum shear stress in this annular shaft with a slit. So, let me call it as tau s. So, what is tau s? We have seen that tau max for an open cross section is given as plus minus g theta into t. So, if we just consider the absolute value, so this is going to be g theta into t. T is the same t that we have here. So, in place of g theta, I can write this as 3t by pi, 3tt by pi into 16t to the power 4, which is 3t by 16 pi t cube. So, this is tau s in case of an annular tube with a slit. Now, let us move into close cross section. So, if it is a close cross section annular shaft, we know that the torque T can actually be written as, which is indeed mt that we have been talking about, or the applied torque or applied torsional moment is going to be 2a into h, where a is the mean area enclosed by the shaft and h is the depth or height of the deformed membrane. So, therefore, in place of h, we can actually write that, we can say that this is going to be, A is going to be pi by 4 into d square. A is the mean area, which is pi by 4 into the mean diameter, pi by 4 d square into h. So, in place of h, we can write this as tau into t, t being constant and tau being the shear stress. We can write this as tau c, c denoting the closed cross section. Now, in place, so if we expand this, we have this as 128 pi by tau c into t cube. Now, from Bed-Pethos theorem, we have tau ds is equal to 2GA into theta, where theta will be theta c, denoting that it is for a closed cross section shaft. Now, tau, because it is a constant thickness shaft, Ts is equal to T or constant, and therefore, tau is also equal to constant. So, therefore, I can, from this expression, we can say that tau c into ds is going to be 2GA into theta c. Now, from here we can say tau c ds is going to be the circumferential length of the cross section, which is going to be pi into d, and that is going to be 2GA theta c. So, in place of tau c, we can write this as 2GA theta c by pi into d. So, this can be substituted here and we can obtain this as 128 pi tau c. In place of tau c, we will write this expression. So, we will write this as t cube. In place of tau c, we will write 2GA theta c by pi into d. So, let us do simplification. So, we can cancel out pi. In place of d, we can write this as 16t. In place of a, we can write this as pi by 4 d square. So, rather this d cancels out, this cancels out with this cancels out with this and becomes 64. So, if we write this, then this should be equal to, the torque should be equal to 64 into d, which is 16. So, we have so if we write it in terms of torque, it is going to be 1024 into 1024 into g theta c into pi into t to the power 4. So, we can say therefore, so I can erase this thing and write it. So, therefore, this is theta c. Therefore, we can write that theta c is going to be torque by 1024 into g into pi into t to the power 4. So, this is one expression that we obtain for theta c. Now, theta s is given as this, where theta c is given in this form. So, we can therefore find out the ratio between theta s and theta c as theta s by theta c as 3t by pi g 16 t to the power 4 into 1024 g pi t to the power 4 by t. Now, if we cancel out and simplify this, so we will get this answer as 24. So, therefore, theta s by theta c is going to be 24. That is the answer 1. Now, we have to find out the expression for tau c and see what is the ratio of the shear stress for both the cross section. So, from the previous cross section, we have obtained that tau s. From the previous cross section, we have found tau s is equal to the 3t by 16 pi t cube, and from the for the closed cross section we have obtained Tc to be equal to G is going to be equal to 8t by 1024 into pi t cube. We can see from the previous thing that tau c, this tau c, if we calculate in terms of t, therefore tau c is going to be t by pi t it's going to be 2 is going to cancel with each other. So, we will have pi into 1024, it's into 128 by t cube. That is what we have got. So, now if we find out the ratio of tau s by tau c, that is going to be 3t by 16 pi t cube into 128 pi t cube by t. So, if you calculate this ratio ends up with 192. Therefore, we see that the same cross section, just in one case there is a simple slit, and because of this slit the torsional property of the two cross section changes drastically. So, we see that for the same torque that is applied to both the cross section, the maximum shear stress developed in the open cross section or the cross section with the slit is 192 times that of the shear stress developed in a closed cross section tube of exactly the same geometrical dimension and the same torque applied. Therefore, we can realize that a open cross section is much more vulnerable to defect under torsion, to failure under torsion as compared to a closed cross section. So, for torsional load we will always prefer a closed cross section shaft as compared to a open cross section shaft, because the strength of a closed cross section shaft is almost 192 times that of a corresponding open cross section shaft. Similarly, we have also seen that not only the shear stress, but the angle of twist is also 24 times more for a open cross section shaft as compared to the closed cross section shaft. So, just a slit makes this huge difference in the torsional resistance of a shaft. So, the moral of this example is that we will always prefer a closed cross section shaft as compared to an open cross section shaft for a structure which is experiencing torsional load. So, we will prefer, if we are having beams under torsional load, we will always prefer to have the beam with a closed cross section instead of an open cross section. But there are aircraft structures where it is not possible to have a closed cross section, and for certain other design requirement, and we will have to stick to closed cross section. We will have to stick to open cross section. So, whenever we face an open cross section, we should be more careful about how it behaves under torsional load, because the open cross section beam or a shaft is more vulnerable to a torsional load as compared to a closed cross section. So, with this I will end this lecture. We will take up further complex problem of torsion of thin wall cross section in the next lecture. Thank you.